All right. So it's my pleasure to introduce our speaker today, Changliu Liu. So Changliu is an assistant professor at Carnegie Mellon University in the Robotics Institute. She received her undergraduate degree at Tsinghua University, her master's and PhD from Berkeley before moving to Stanford as a postdoc, and then to CMU as faculty. So Changliu's research is on the safe control of autonomous systems. She's made a bunch of really exciting contributions to formal verification of autonomous systems, robots specifically, and systems that have kind of neural network components, so doing verification for neural networks. And I think we'll see maybe a little bit of that work today. So she's received a number of awards for her work, including the NSF Career Award, the Amazon Research Award, Research Award from Ford, and multiple Best Paper Awards at many conferences. So Changliu, it's a pleasure to have you here. Thanks for taking the time. We're looking forward to the talk.
Thanks, Andy, for the great introduction. Hello everyone, I'm Changliu. And today I'm going to share with you some of our recent work on ensuring robot safety, providing formal guarantees through a technique called safety index synthesis. Okay, I'll start with some fancy robot videos. So our work, we're trying to build mathematical tools to solve real-world problems. And the real-world problems we're trying to solve is how can we make robots safer and more efficient to work with humans. So for example, in this situation, the robot can help human assemble a IKEA furniture. In order to achieve that, the robot should understand the human's command, like human's pointing. When the human's pointing, the robot should deliver the tool. And when the tool is not delivered in the correct direction, the human will do some gesture command, and the robot should understand that and also remember that command in the future so that they will provide better assistance to the human. So that's one aspect of the problem that we're looking at. But in order to achieve this smooth collaboration, the foundation of all the foundation is safety. How can you make sure that the robot will never generate harmful actions towards the human? So for this one, it's a bit long. Let me directly jump to the end. So you can see with our algorithm, the robot is able to help the human with this furniture assembly. And in the end, we get a nice drawer out of this collaboration. So that's one type of application of our work. And recently, we also started to look at like robot, not only the robot manipulation, but also, I probably need to get online.
Okay.
Yeah, but maybe we can get back to this video later. Yes. Yeah, we also look at lagged robots, which this is a recent video my student Tairan just released. In this video, we made the robot dog run very fast, up to 3 meters per minute, or per second. But at that high speed, safety is another huge concern. We don't want the robot to hit any critical objects in the environment. Don't want the robot to hit human. So then we did this safe training of the robot dog such that it knows how to keep the speed while avoiding collision. Yeah, and I think this one probably also needs online access. Yes. Yeah, and recently we're also trying to combine all the manipulation work with the local motion work into this humanoid robot, which we have both the arms and the legs. With the current kind of development of humanoid robots, I believe this is the best time to study human-humanoid collaboration and interaction. And this marks our first effort along this line, which is like a naive interaction. Since the humanoid is actually being teleoped by the human, there's no direct collaboration. The humanoid is trying to mimic the human's action. There's a lot of issues. For example, there's a mismatch between the human dynamics and the humanoid dynamics. But through learning approaches, we were able to transfer the motion and let the humanoid copy the human's motion in real time. But safety is also a huge concern in this situation. The humanoid needs to make sure that it will always stay stable while copying human's motion. And also later, if we want to make the humanoid to directly collaborate with the human, for example, in this boxing case on the left, we want to make sure that, okay, this is not collaborating, this is fighting, but still, this safety constraint exists. The humanoid should not hit critical part of the human body. Yeah, so that's all the motivations for safety and how we look at safety. For safety, we mathematically see it as a constraint satisfaction problem. And the safety specification, considering our work, are those state-wise constraints, which are a closed set defined on your system's state space. There can be other type of safety specifications, for example, temporal logic specifications, that can encode like more complicated behaviors of the robot. But for today's talk, I'm going to be focused on the state-wise constraint. And then what are the problems we want to solve? The first problem is called forward invariance. We want to synthesize a set of control rule such that if the system starts within this safe set or the safety specification, then the system will never leave it, or the future trajectory will stay within this set. And sometimes we also want a property called finite time convergence. That is, if the system happens to start outside the safe region, can we synthesize a control rule such that it will go back to the safe region in finite time? I will touch a little bit on the finite time convergence, but most of the talk will be focused on this property of forward invariance. Yeah. So how can we deal with forward invariance in a naive way? The most naive way is just to pose this as an infinite horizon optimization. So we want to optimize some objective function, J, that depends on your system trajectory, which starts from time 0, goes to infinity, such that at every point on your trajectory, it will always belong to the safety specification XS. Yeah, so if you can get a good answer for this problem, either you find a trajectory that satisfies this constraint, or you find a policy such that no matter what distance you get, you can always pull your system back to satisfy this constraint, and then you're done. But the problem is that since this is an infinite horizon problem, it's very challenging to solve, especially if your dynamics are nonlinear and also there are uncertainties in your system. So then, what are the practical approaches to deal with those infinite number of constraints? The core idea in, I would say, most concurrent research is to bring the finite time horizon problem into bring the infinite time horizon problem into some finite time horizon, and then solve those in finite time, then deploy back to the infinite time. What does this mean? This figure is a very typical MPC figure. I borrowed it from MPC textbook. But I would say a lot of control paradigm actually uses this idea. That is, you have two different time domains. One is the virtual time domain, one is the actual real time domain. In the virtual time domain, you do the computation. And you can look ahead no matter what number of steps you want to see. And then get your desired control policy or get your desired state. And then you deploy your solution to the real time. While during the deployment, you can compute another kind of plan into the future. And then once the other plan is computed, then you can deploy it, and then you can compute another plan again and again. Yeah, so the advantage of doing that is we can break down this infinite horizon problem into several finite horizon problems and solve them repeatedly once we progress. But then the question is, if we do this kind of finite horizon computing, can we still use the same constraint that we had for the original infinite horizon problem? Yeah, obviously the answer is not. Here's a very simple example. Suppose we have a vehicle here, and there's an obstacle in front of the vehicle. We want the vehicle to stop before hitting this obstacle. The vehicle is a second order system, so that means it can directly affect its acceleration. And the state is taken as the vehicle's velocity as well as the vehicle's distance towards the obstacle. And we have an acceleration bound of the vehicle. That is, we cannot apply more deceleration than this -10. So given this problem, we can plot this phase portrait as shown on the right. The horizontal axis of this phase portrait is the distance from the vehicle to the obstacle. The vertical axis is the velocity towards the obstacle. And there's a dynamic limit. That is to say that if you apply the maximum amount of deceleration, then the fastest you can decelerate is along this curve, this red dot curve. which means if you're below this red dotted curve, then you are able to stop in time. If you're above, then there's no chance for you to stop in time. So that's the theoretical limit. But if we naively apply that finite horizon optimization that we show in the last slide, what will happen is that suppose you start from an initial point here, and then here we take a preview horizon of 2. We look at 2 steps ahead, and okay, those 2 steps, if we keep the same speed, then no collision will happen, so then we can safely apply that. And then at the next step, we look 2 steps ahead again, okay, safely apply. We will only be affected by the original infinite horizon constraint at a point here, where if we start from this point and apply the same velocity, then we'll hit the wall. And then at this moment, the optimization will tell us, okay, now you should slow down. But at this point, it's too late. Yeah, so this is the infeasibility problem, happens a lot in those receding horizon control. It actually does not matter where you start. If you start here, similar things happen, start here. At every point, you'll get into this collision. So this infeasibility problem can be solved if you extend this preview horizon. So for now, this preview horizon is too short, n equal to 2. If you extend it to, for example, 100, then in this example, this infeasibility will disappear. But that is not a systematic way to solve this infeasibility issue. And in literature, there are 2 systematic approaches to solve those infeasibility. The first approach is called control invariance. What does it mean? The core idea of control invariance is that we should find a so-called control invariance set inside our original safety specification. And a control invariance set is a set C such that if your system state is currently in C, then it is guaranteed that there exists a control in your control limit such that your next step, your system state in the next step will still be belonging to C. Yeah, so this is a invariance that means you can always stay inside C. And once you have this control invariance constraint, then the finite horizon problem, we don't need to look very far into the future. We just need to make sure the next step state stays within C. And because of this control invariance, we can ensure, okay, all the future steps will also be inside C. And typical approaches for, or typical methods under this general approach are control barrier functions and safe set algorithms. That is especially the one that I'm going to talk about. And before we look at more mathematical details, let's look at one example on how to compute this control invariance set. Yeah, so we just take a very naive parameterization of the control invariance set. We just want to do a linear combination between the distance and the velocity to form this control invariance set. And we know that the maximum deceleration is -10. And then in this problem, our system state is bounded by distance of 10. That means if we pose the constraint -d plus v smaller than or equal to 0, pose this constraint as the control invariance set, there always exists an acceleration to keep our system, the next step's state, inside this constraint. Yeah, that is because d at most is 10, and then we can do that deceleration of 10. Okay, so then this is then our forward invariance set, which is the red part. Yeah, and one more thing, the reason why we got this discretized representation of the forward invariance set is not because our computation method is discretized, it's just because of visualization. The set itself is a continuous set. Okay, so then with this constraint, now let's do the trajectory generation again. So suppose we start from here, which is inside the forward invariance set. We look one step ahead. Okay, we're good. There's no violation of the forward invariance set, then we are good to apply this constant velocity. And we apply constant velocity until this point. At this point, if we look ahead, the constant velocity will violate the forward invariance constraint. Then we modify the constant velocity action to generate a small deceleration and keep the system still within the forward invariance set. And then that actually brings us to the boundary of the forward invariance set. At the boundary of the forward invariant set, we always choose the action that keeps us on the boundary. And then finally, we decelerate to velocity 0 before hitting the obstacle. Yeah, and similarly for other states, we can still guarantee safety. But admittedly, if we start outside the forward invariant set, although this state, as we said, it is kind of feasible, it could be made safe according to our dynamic limit. But because of the type of constraint we construct with this control invariant approach being more conservative, so then using that constraint, we actually would not be able to make the system decelerate enough before hitting the obstacle. That's one limitation of those control invariance approach. That is, the set of forward invariant set, the size of the forward invariant set highly depend on how you parameterize your this essentially safety forward invariant set. Okay. Yes.
So I guess I'm trying to figure out whether the issues with the fact that you're using a control invariant set, and you have this constraint that you remain within the control invariant set, or whether it's just the particular control invariant set that you chose. I guess, I mean, could you, is the thing that's the set that's the bottom right of the red curve? Is that also a forward invariant set?
Yes, you can make that a forward invariant set. That's what I'm going to show 2 slides later.
Okay, sounds good.
Yeah. Okay. Yeah, but before that, let's look at the second approach, which we have an expert Jaime here. The second approach, we call it as constraint aggregation. The core idea is to leverage the so-called Bellman update to find a value function for your constraint. So for Bellman updates, people usually use that to find a value function for your reward, which is relatively soft, but we can use the similar idea to find the value function for the constraint using something like the equation shown here. What does it mean? So V here essentially tells us what is the maximum violation in all your future trajectory. Yeah, so it equals to the maximization of the current violation. This phi 0 denotes how much you violate the original safety spec. And we take the maximization over the current violation as well as the future violation. And then we will consider the minimum possible future violation because we can choose the control to avoid larger violation. So we do this mean over control. Okay, so then we can do like a recursive update to this Bellman equation. And this is called constraint aggregation mainly because if we follow the conventional Bellman updates, we are essentially doing some backward propagation to propagate the maximum possible violation in the future towards the current step. And after we get this value function, then we can enforce the value function to be smaller than 0 in the next step. And representative methods are the Hamilton-Jacobi reachability approach. And also, we find this cost value function approach in the constraint Markov decision process also follow the similar paradigm. Although the difference is that in order for the cost value function to converge in CMDP, they usually introduce a forgetting factor. So it is not an exact kind of maximum violation in the future. All right, with that, let's look at one example by applying the HJ reachability in our toy problem. So in the HJ reachability, there are, as far as I know, at least 2 different approaches to compute that. One is the grid-based approach, one is more learning-based approach. But in this simple 1D problem, actually, we can just solve this Bellman equation using like an analytical approach. And the final solution for the value function is essentially this one. Negative d minus v squared over 20 equal to v. And then v should be smaller than or equal to 0. Why is that the case? So this one is essentially the motion of the Newton's law, Newton's second law. That means the distance at the future equals to the current distance plus the velocity squared over the maximum acceleration. That's the worst case distance. And the maximum deceleration, maximum deceleration is 10, and then multiplying 2, it's 20. And so then this one gives us the optimal value under the HJ reachability. And essentially, this one is exactly the same as the dynamic limit we can compute. So then, with HJ reachability, if we compute it exactly, it will give us the optimal or maximum forward invariant set. And with this modified constraint using HJ reachability, if we start from anywhere inside this forward invariant set, we can make sure all the trajectories will be kept inside the constraint. Yeah. So then we no longer need to account for all future time steps. We just need to use the HJ reachability to do the pre-computation and then use the constraint inside the real-time computation just for next step. All right, so then you may think, okay, HJ reachability is so strong. Why do we still care about control invariance? That is because for HJ reachability for this type of simple problem, it's easy to compute, but if you scale it up, there's still a lot of computation challenge. And for control invariance, the good thing is that we can arbitrarily parameterize the control invariant set. And in our previous work, we have already found a very good function class to describe the control invariant set for all kinds of collision avoidance problems, which is shown here. For any second order system with specification phi 0 equal to d mean minus d smaller than 0, we can parameterize the safety index as the following, which we first add a constant to adjust the conservativeness, and then take this d mean and d both to the n power to nonlinearly shape the boundary of the constraint, and then add a penalty on the velocity so that we can make sure that even the acceleration is bounded, we can stop in time. All right, and using this parameterization, by properly choosing the parameters n and k, in this case n equal to 0.5, k equal to 0.23, we can actually achieve the maximum forward invariant set, which is exactly the same as the set that we get using HJ reachability analysis. Yeah, and with that, we can then apply the constraint, and finally we'll see that all the trajectories will be made safe. Yes?
How do you know that n, k, and c in this case?
Yes, that's exactly what we are going to talk about, how to synthesize that. Yeah, so, and we've already seen that using this parameterization, there's not many parameters to optimize. It's just 3, c, n, and k. Yeah, and in the following discussion, I'm going to talk about different ways to synthesize that, which we believe is easier than to synthesize a value function in the HJB case. And also, in the case that we want this safety index to be more expressive, meaning that describe more details on the boundary, we can also replace this constant term with a neural network. And that will give us a neural safety index, which in our previous work have been shown to perform very well. Then naively parameterize everything as the whole safety index as a black box end-to-end neural network. All right, before we get to the synthesis of the safety index, let's look at some history of the SafeSat algorithm. So this SafeSat algorithm was first introduced in 2014 while I was doing my PhD at Berkeley. We were at the beginning trying to solve safe human-robot interaction problem. That is, we want to make sure that if a human is interacting with a robot, then any part of the human body should be kept some distance away from the robot body. And we use some a simplified geometric representation of both the robot and the human, and then pose the mathematical constraint for the collision avoidance. But this problem is actually slightly more complicated than the safety index problem or the safety index we introduced earlier, in the sense that this problem also contains a lot of uncertainty from human. And the robots can only affect its own state. It cannot directly affect the human state. So then in our previous work, the SafeSat algorithm contains 2 parts. The first part is that we will actively predict what the human will do at every time step, and then based on the prediction, decide what the robot will do. Yeah, and in this case, our safety constraint is the blue region. If we predict that the human will go up, then the robot should go to the right in order to stay safe. And then in order to make this more computational friendly, we then introduce the safety index to tell us which type of action is safe. So for all the action that makes the safety index go above this level set is unsafe, which the level set essentially coincides with the blue region, that is the collision-free region. And then all the control that brings the system down towards the level set are safe. Yeah. And with that notion, we can then construct the actual control constraint by plugging the system dynamics. Here we assume the system dynamics are control affine in the sense that this x dot is a combined human and robot state equals to some inertia term fx plus some control affected term gx multiply u. Yeah, you may wonder how can we model human-robot dynamics into this form. It's actually very easy. You can first model the robot dynamics, then model the closed-loop human dynamics, see how it will be affected by the robots, and then make the closed-loop human dynamics into this F term. Yeah, and then we'll come up with this model. Once we have this model, then we can apply the rule that we get. So the rule is we need to check the change of the safety index to see if the system, if the control is safe, is good to be applied or not. And the change of the safety index can be described by taking the derivative phi dot. Yeah. So then phi dot equals to the partial derivative from phi to x multiply x dot. And if we expand, we get those Lie derivatives. And in order to make sure the control is good to be applied, we constrain this phi dot by some constant depending on the current situation. So if currently our safety index says we're safe, then we can relax this constraint a lot. If it says we're currently unsafe, then we need to make this much more negative constant so that we can go back to the safe set faster. Yeah, and then with this constraint and plugging the expression of phi dot, we will get a constraint on our control. Once we get the constraint on control, then we can just apply this constraint and use it to monitor all kinds of task-oriented controllers we have and project potential unsafe actions from the task-oriented controller back to the set of safe control that satisfy this constraint. Yeah. And we can do this using quadratic programming. So the whole process here is actually very similar to control barrier function approach if you're familiar with that. And the only difference between safe set, or not the only, the biggest difference between the safe set algorithm and the control barrier function approach is in the choice of the constraint. Where the control barrier function approach chooses a continuous constraint function here, and in the safe set algorithm, we get more inspiration from the sliding mode control, which is a band control type of discontinuous control. So then we choose this continuous constraint here. And all other steps are very similar. Yeah, finally we get this projection, and once every step we can do this projection, then we can guarantee the system is forward invariant. And a more concrete example is shown here. Suppose we have a human carrying a large ladder passing our robot. And the human probably didn't notice that there will be a potential collision. So if the robots keep the same location, it is actually unsafe. And by calculating that, the robots will modify its action by rotating it a little bit, which this exactly is the, in the control space, is exactly mapping the original normal control to the moving forward control in order to stay safe. All right, so that's the big idea, general idea of the safe set algorithm. But you may wonder, then in this case, everything seems to work if we have a good safety index, but everything will break down if we do not have a safety index. Then I would say the biggest contribution in our previous work is that we proved the Furlan theorem. So if you have a safety spec, xs, defined as phi 0 smaller than or equal to 0, then we can define a safety index in the following form, which equals to some phi 0 star plus some linear combination of the higher order derivatives of your original constraint, where the roots of all those coefficients for the linear combination are all negative real. This is to make sure that as you add in higher order terms, your system will never overshoot going away from the safety boundary. And then the second constraint is that this phi 0 star should describe a smaller set than your original safe set. And once these two conditions are satisfied, then we can say a subset of the 0 sublevel set of the new safety index intersecting with the original safe constraint is forward invariant if you can enforce the following control law. That is, whenever we are touching the 0 level boundary of the safety index, we apply a negative control, decreasing the value. And also, this subset can be made finite time converging if we can even apply harder control, like a more decreasing control once the system is on the state which safety index is your dangerous, your positive. This is very mathematical, but let's look at some graphical representation. So here, our safety index, phi 0, is shown on the horizontal axis. And then the derivative of phi 0 is shown in the vertical axis. So then this is a kind of also a phase portrait that can be used to analyze your system's property. So originally, our requirement is for the system to always stay on the left side of this plot. But if the system has dynamic limits, for example, your system can only be affected through the acceleration term, not the velocity term, then for all the states along this axis will never be made safe. That is, if you're already here, no matter how hard you decelerate, how hard you control, you'll always go to the positive part of phi 0 because currently phi 0 dot is positive. Yeah. And if you think about the previous collision avoidance problem, it's also the case. You need to decelerate much faster, or you need to kind of decelerate way before you hit the boundary of like a distance equal to 0. So in order to then get rid of this part, we introduce this linear combination of the higher order terms. Yeah, so just by adding one higher order term, adding this k1 plus phi 0 dot, we can remove this part. And then our kind of forward invariant set, if it can be made forward invariant, will be a much smaller one. And we can also do nonlinear shaping of this boundary by replacing the original phi 0 with this phi 0 star. And in the end, it becomes this new forward invariant set. Yeah, and this example considers essentially second order system. And in second order system, the condition is actually a little bit stronger, which says the forward invariant set after doing this type of synthesis is exactly this intersection, which is not a subset anymore. It's exactly this intersection. For even higher order systems, for example, third order, fourth order, like used a lot in drone and also some jerk control system, this equivalence is not there yet. Yeah, but for second order acceleration control system, there's an equivalence. Yeah, and also it's easy to check. The safety index we introduced earlier exactly matches this parameterization. You can view this part, c plus d mean to the n power minus d to the n power, as this phi 0 star, which describes a little bit more conservative constraint than the original constraint. And then this kv part is the kind of derivative parts of the original safety spec. All right, so that's the history. You may wonder, in this theorem, we actually only says if something happens, if there is a control. But how can we make sure there is a control? Yeah, so how can we achieve those realizability of these conditions under control limits? That's the challenging part, and that's essentially the research that I have done starting in 2019, and recently we came up with a lot of approaches to improve realizability. Okay, so a little bit more on the realizability. Realizability is essentially whether you can find a control that decreases your safety index, that satisfies your constraint. Yeah, and why realizability is that important? Let's still look at the example, but with a slightly more complicated situation. In the first example, we're looking at 1D collision avoidance. Now we look at 2D collision avoidance. Yeah, that is, we have this vehicle, also second order. It wants to avoid some like obstacle. And then we can still parameterize our safety index as the following. So if we do not properly choose the hyperparameters c, n, and k here, we will not be able to realize the phi dot smaller than 0 condition. Yeah, so for example, we just set n to 1 and then the k to 0. Then the safety index reduces to the original safety spec. And in this case, if we check the states x1, x2, x3, x4 here, for each state, we see if there exists any control that satisfies the phi dot smaller than 0 or smaller than this negative eta constraint. We find, although we can find some feasible control for state x1, x3, and x4, there is no feasible control for x2. And the reason is very obvious. At this stage, we are not able to kind of maintain this state within this boundary. It will eventually breach into the unsafe region because we have the acceleration limit. Yeah, and then if we properly select the hyperparameters of the safety index, then it corresponds to the shaping of the boundary of the forward invariant set. And with this new shaping, then all the states will have some feasible safe control as shown in the green region. Yeah, although the problem in this case is that for state 3 here, there exists some feasible safe control as the green region, but the intersection between the feasible safe control with the control limit is too little. And that will greatly limit the degree of freedom of the system while we are doing some like a dangerous maneuver or extreme maneuver. Then we want to further optimize our safety index so that for every state, the feasible safe control intersecting with the control limits is some non-trivial region. Yeah. And this whole process, we call it as the safety index synthesis. All right. Yeah, let's then provide a formal definition of safety index synthesis. So formal definition is that we want to find the parameters for the safety index in the following form. Yeah, here it is assuming we have a second order system. If we have higher order system, we can then add additional terms. Yeah, but for the second order system, we want to find the parameters c, n, and k in the safety index such that this condition phi dot smaller than or equal to some negative eta phi is always realizable under possible control limits and also possible uncertainties. And then the realizability condition is that the set of control that satisfy this inequality intersecting with our original control limits is non-empty at every state. Yeah, and with this notion, then we can easily formulate this safety index synthesis problem as the following optimization, which we can first find the worst state such that this intersection in the control space is the smallest. That is, it's the hardest for us to find a feasible safe control. And then we can optimize this worst case condition by properly choosing the parameters of our safety index such that this worst case intersection become larger. All right, great. We're done with the formulation, and I will then quickly go over the different approaches to solve this optimization. So altogether, we have explored 5 different ways to solve this problem, and they both have pros and cons. Yeah, I'm just going to provide a high-level overview given the time. So the first approach we explored is a rule-based approach. Yeah, that is because as we are looking at like a 2D collision avoidance, like vehicle collision avoidance, we find this problem is easy enough for us to directly derive the constraints on the hyperparameters such that you always get realizability. Yeah, and how we did this is that we first kind of replace this inner minimization with a different objective because the evaluation of the size of a set is challenging if you do analytical derivation. But the objective can be equivalently achieved if we just make sure that phi dot can be made negative. Yeah, if phi dot can be made negative, then that means there exists some control that we can go back to the safe region. Yeah, so then we replace this one with max negative phi dot, so the negative the better, and then still take the mean over x. But here, instead of maximize over the whole state space, we just look at the boundary of the safety index and make sure that on the boundary, we can always push the system state back towards the interior of the safe region. Yeah, and with this new objective, and with the understanding that we can easily compute the distance between the vehicle and the obstacle and the relative velocity and also relative deceleration, we can then plug everything into all the expression into this phi dot term. Yeah, so phi dot is a derivative of this expression, and then we can plug in the analytical form of d dot and d double dot, and then after some lengthy derivation, we come up with this condition. That is, if your hyperparameters satisfy the following inequality, then it is guaranteed you will have a forward invariant safe set. And here we need to have some like a control, some limits on the velocity as well as the limit on the acceleration. Once we get those, then we are safe to go. Yeah, and later we find this approach not only applied to unicycles as shown here, it actually applies to any 2D collision avoidance problem as long as there's a surjective mapping from the control space of the specific robot you have to the control space of the unicycle. Yeah, but although this is easy, the problem is that it does not generate to 3D. Yeah, it only stays in 2D. In order to generalize, we then started to look at more kind of automatic approach to do the synthesis, essentially to solve the minimax optimization. Yeah, and the first approach we tried is this evolutionary optimization. Yeah, which we apply evolution on the max, and then we apply grid-based sampling on the mean. Yeah, so what we do is that we first evaluate the inner minimization by taking a grid sampling of the state space. If your dynamic system is Lipschitz continuous, then, and also if your sample state has some non-trivial feasible control, then that means some neighborhoods around that state also have some non-trivial kind of feasible safe control. In that case, we do not necessarily need to check the infinite number of states. We can only check the finitely many grid samples. Yeah, so that's the idea. And that can be used to evaluate the inner minimization. And then the outer maximization can be done using evolutionary optimization. Specifically, we use CMAES, which is a derivative-free method for numerical optimization. What it does is it will initiate a lot of samples to try to evaluate, and those samples are the essentially parameters of the safety index. And for each sample, we'll evaluate the minimization and then give a different weighting of the sample, and then we resample the weighted new samples, and then regenerate a new evaluation, and then until we converge. So in this approach, it actually works very well in relatively low dimensional systems. For example, we evaluated this on a planar robot as well as a Segway. The figure here is showing before optimization and after optimization. So before optimization, we naively select the parameters of the safety index. And then there are a lot of locations on the state space which does not contain a feasible safe control, which is not realizable. But after optimization, everywhere is realizable. And this optimization is done within actually several minutes. Yeah, but the problem is still, how can we generalize to higher order systems, especially robot arms, which we usually have at least 12 degrees of freedom? If we sample the 12th degree of freedom using grid sampling, that's a huge burden. Yeah, and we recently come up with an abstraction approach. So for example, if we are not doing the full body collision avoidance, but only doing this end-effector collision avoidance, then essentially the dynamics for the robot does not matter that much. We can then abstract the robot itself as a control constraint for the n effector. And then n effector has only like a the n effector only have 3 states that we model. And then the control limits abstracted out from the robot arm only have 1 parameter. And then within the 4-dimensional space, we can easily do this evolutionary optimization. Okay, but then another limitation of evolutionary optimization is that in order to optimize, we need to uniformly check all the states. But do we actually need to do that? Should we care more about the states that the robot will actually visit? Yeah, and that motivated us to explore this synthesis using reinforcement learning. Yeah, because in the end, we want to safeguard the policy. So then we only want the state that will be visited by our policy to be safe, to be realizable. So then what we do is to modify the learning objective of your reinforcement learning algorithm by adding this safety constraint through this Lagrangian term. Yeah, and this Lagrangian term is slightly different from the original PPO Lagrangian in the sense that it is dependent on the state x. Yeah, so it will create a filtering such that if the current state is safe, according to your safety index, then this constraint will disappear, this whole term will disappear. If it's unsafe, then this whole term will become a very large value in order to encourage your policy to converge to the safe one. Yeah, and then this multiplied term is computing the increase of the safety index from the current step to the next step. We essentially want to make sure there's no increase of the safety index towards the positive. Yeah. Okay, it's more complicated. So if the current safety index is below 0, then we want the next safety index to be also below 0. But if the current safety index is a very positive value, we wanted the next step safety index to at least decrease the current safety index by some negative eta. So then that is going towards the safe region. Yeah, and then we can do a multi-layer learning, also leveraging the framework of the adversarial optimization. That is, we first optimize the policy as well as the Lagrangian multiplier in order to make sure the current policy will be aligned with the current safety index. And then we optimize the safety index to make sure that on the current trajectory, we are properly evaluating the safety potential. And then we do this iteratively, and we have proof that in the limit, it will converge to the case that along all the trajectories generated by the learned policy, the safety index will never increase to positive part if we start from the safe region. Yeah, I'm going to probably fast forward this. So these slides are just to say that we evaluate this approach on the safety gym, and it works very well, much better than the existing safe RL approach. I'm going to spend more time on this slide. Yeah, this slide essentially says, visualizes the final learned safe set using this combined reinforcement learning approach and compare it with the safe region computed using Hamilton-Jacobi reachability. Yeah, so let's look at the problem. The problem is due to the 2D collision avoidance. We want this robot to avoid this obstacle. Yeah, and then if the robot's current angle is 90 degrees, then this direction is more dangerous. And maybe this direction? Yeah, then we need to avoid that harder. And the HJ reachability tells us that if currently robot is 90 degrees, then we should avoid this region inside this red contour. Using our approach, we synthesized this green contour, which is a proper, like a safe region because it already contained all the unsafe part, which is provided by the ground truth of HJ reachability. So that's good. Although it's a little bit conservative, but given the fact that we are constrained by the function class, that is acceptable. If later we can change to neural network parameterization, it will be less conservative. Yeah, and another contour is the gray one, which is a naively parameterized barrier function. It actually, without learning, without this optimization over realizability, it actually does not properly account for all the dangerous situation, in the sense that in this region, it is outside the contour, so then that means barrier function says it's safe, but actually HJ says it's unsafe. Okay. Question?
Well, I was wondering, so what is happening then? How is that possible? Because HJ gives you the maximum invariance.
Yeah, so that is because it is not synthesized, not optimized. Without optimization for reachability, naively applying the barrier function approach or safety index approach will not guarantee 100% safety.
Oh, I see. So this is not, it's not yet, you haven't yet done the certification, so there's just an approximation for now.
Yeah.
Okay.
Yeah, but after optimization, yeah, we will get like a conservative estimation of the unsafe region. All right, and another question we are thinking about after doing that is that learning using reinforcement, like learning according to the distribution of the state is good, but it's still time consuming. Can we directly attack the boundary of the full invariant set and make sure that we can converge faster? Yeah, this is exactly what my student Siming did 2 years ago. So she found a very interesting approach to sample high-dimensional manifolds of the boundary of the safety index, and then attack the manifold by sampling along this boundary, and then use the critic learner or adversarial learning approach to gradually improve your safety index such that by attacking the boundary, there is no violation on the boundary. Yeah, and using this approach, she successfully learned a neural safety index, which scales to 10-dimensional state and 4-dimensional control, which I believe is still the state of the art for any type of like a neural network-based barrier function or safety index. And the reason why it scales, not only because her approach in attack is very efficient, but also because the parameterization is very efficient in the sense that the neural network parts is only used to learn this like a bias term, while the other high-dimensional dynamics are already embedded to the parameterization. All right, and the last piece of work I would like to briefly mention is that all of the previous ones are doing sampling in order to sampling on the state in order to get a proper safety index. But can we go without sampling? If we want to go without sampling, then as far as I know, there's only one approach we can do that, which is called the sum of square programming. And the idea of sum of square programming is that if we want to test a condition is satisfied for infinitely many possibilities, we can turn this problem into a refute set. Yeah, so for all x, fx greater than 0, in order to prove that, we can prove that fx smaller than 0 is empty. Yeah, and if we can prove that, for the second condition, we can then turn it into some like a positive definite constraint. And in our problem, if we want to synthesize a safety index for a robot arm, we can do exactly the same, following the same procedure. Yeah, so here the math is a little bit lengthy, but let me see if I can, how long do we have? It's already 12.
Yeah, we usually go 5 minutes or so.
Okay, cool. Let me finish this in 2 minutes. Okay, so if we want to do collision avoidance for this 1D robot arm, assuming it has length 1, and its states are constrained, acceleration is also constrained. It's a second order system still. The state is the angle and the angular velocity as well as the acceleration. The safety requirement is that it does not hit the wall. The cosine theta minus 0.5 smaller than 0. And then following our design rule, we design a safety index as the following, just adding one higher order term. And then we want to make sure this phi dot can be always made negative. along the boundary of the safe set. So then with all of these, we can encode the following 5 constraints. The first constraint is that phi dot smaller than 0. Second constraint is the second and third is the theta constraint. And the fourth one is the theta dot constraint. Fifth one is the constraint that we are only checking the condition when phi equal to 0. All right, once we have those constraints, we first need to make the sine and cosine term disappear. And we can just do a substitution of variables. And because of this substitution, we need to introduce one more condition, that is sine squared plus cosine squared equal to 1. After that, we can then construct the refute problem, which is just pick one of the inequality and flip the sign. Yeah, so we flip this sign here. And once we do that, then we can try to use sum of square programming to prove this refute set is empty. And to prove that, we just need to find some sum of square polynomials and also some ordinary polynomials such that the following inequality satisfy. Yeah, and if we just look at those inequality, maybe let's ignore the Q1, Q2 parts because H are zeros, so then let's ignore that. So if we cannot find those sum of square polynomials that this satisfy, then it means at least sum of F1, F2, F3, or F4 could be made negative. Yeah, then that refute set is not empty. But if we can prove this sum of square polynomials P0 to P4 exist, then all the F's must be, if we prove that exists, then that means all the F's cannot be always positive, which is exactly our objective. And we can then encode all of these using the conventional sum of square solvers and get our final solution for all the polynomials as well as the safety index parameters. All right, that's a very brief introduction of sum of square. Yeah, but I think this figure is most important. I would say a lot of people may think sum of square is very inefficient, but actually in our study we find it's very efficient if we properly kind of parameterize the p's, the polynomials. Here, if we use that idea to solve like a robot arm collision avoidance problem, it only scales in the log term with respect to the number of links we have. So very efficient. All right, that's essentially everything. Yeah, so today, yeah, it's my great pleasure to introduce this safety index idea to all of you. Actually, this is also the first time I do more mathematical discussion of the safety index. Previously, we were just talking like we have the safety index. Now here's the human-robot collaboration problem, and let's look at the problem directly. Yeah, but I find the maths behind it is also very interesting. And yeah, we have different ways to synthesize that. Both have pros and cons. Some have guarantees, some not, and some is more efficient, some not. Yeah, and what are the next steps? We are currently trying to build a benchmark to benchmark against all the different safety approaches. We have done a lot, and we are going to do the HJ reachability pretty soon. And this benchmark can do like a normal safety evaluation as well as the safe reinforcement learning stuff. Yeah, and also for those safety index or barrier function that is embedded in neural networks, we want to formally guarantee that they're safe. So we are introducing the neural network verification into the problem. And also we are organizing the international verification for neural network competition. This is the 5th year. We are soliciting benchmarks. So if you have neural network in your system and you want to make sure that is always satisfying constraints, please consider sending a benchmark to us. We have a lot of people building wonderful tools to do the model checking, but we need problems. Yeah. Cool, great. With that, I would like to thank you everyone and happy to take any question.
Yeah, maybe we can take a question or two from the audience.
Yes.
Thanks, Changliu. This is super cool. It's really great to see all of these different synthesis methods and how you can ultimately bring it together to learn these functions. So I wanted to ask you, because this is ultimately, we have all of these many schools of thought within safe control, and so on, but they're also sort of kind of connected, some to others. And so, in a sense, the safety index, the control barrier function, the safety value function, they're trying to get at the same thing, which is understanding whether we're going to violate the constraints in the future. How do you think of sort of the relative advantages? I'm very curious, especially because in your formulation of the safety index, you have this much more flexible function, a dial to x in principle, where you can sort of choose how you do this gradual regulation of the control as you approach the safety boundary. And I'm curious, sort of, what are your thoughts in terms of the relative advantages, what that can allow you to do, and sort of how that connects to other synthesis methods, and similarly, how do these then? Because a lot of the stuff that you're introducing could be used to synthesize barrier functions or approximations of the safety value function.
Yeah. So that's a great question and great comment. There are a lot of points I would like to try to address them like one by one. So first, I think these approaches are almost readily to be used to synthesize control barrier functions because I usually view the safety index as just a nonlinear variant of the high order CBF. Yeah, and the fundamentals are very similar, so then they can be easily used. They are not ready to be used to synthesize value functions yet because of the fundamental mechanism. The safety index is more control invariant and the HJ stuff is more constraint aggregation in the sense that it uses this backward propagation idea, right? And also the parameterization advantage of the unique parameterization we have. In a broader sense, I think that's can be viewed as a neurosymbolic approach, which you inject prior knowledge in your parameterization to ease the synthesized problem. Yeah, and for now, the parameterization essentially ease the treatment with high order dynamics. Maybe later we can introduce additional terms to deal with the noises, uncertainties, as well as maybe some LTI, LTL, linear temporal logic type of constraints. That's all doable, although we don't know yet. Yeah, so from that sense, I would say the future, I believe, in order to create a unified solution for constraint satisfaction in the infinite horizon, would be something along the line of doing neurosynthesis, but injecting prior knowledge through this neurosymbolic approach. And this neurosynthesis can take different objectives. For example, the HJ's objective would definitely be one that can be used. And the for the invariance objective, that is, if you're currently safe, then next step you should be safe, can also be used as a training approach. And in terms of which objectives is better, that still, I think, still require further study. But I do need to say that especially for the HJ synthesis and also the cost value function in the CMDP approach, we cannot get rid of this discounting factor, although this discounting can be almost set as one. But if we have the discounting, then it's hard to do the formal guarantee. How can we get rid of this discounting? Can we leverage some of the objective from the control barrier function approach to improve the synthesis using this constraint aggregation? Maybe also interesting to explore.
Yeah, those are all awesome points. I absolutely look forward to discussing with you later, but we should let other folks ask questions.
Yeah, I guess maybe in the interest of time we can stop here, but Changliu will be at the Robotics socials. If you have more questions, feel free to stop by and chat with her then. Thanks.
Cool, thank you so much.